So, hello everyone. My name is Jing, and I am a PhD candidate at University of Virginia. Today, my talk will be about graph counterfactual fairness. So I will first try to introduce some background about fair machine learning and fairness on graphs. And then most of the content of my today's talk will be based on our wisdom paper this year named Learning Fair Node Representations with Graph Counterfactual Fairness. Nowadays, graphs are everywhere in our life, and graphs have been extensively used for modeling a lot of real-world systems with connected units like social networks, collaboration networks, or knowledge graphs. Recently, machine learning on graphs is developing at a very surprising speed. So especially powered by the recent progress of graph neural networks or GNNs. Machine learning on graphs can be applied in different tasks in graphs, like a recommended system. We can model the user item interactions with a bipartite, and a link between a user and item correspond to whether this user would be interested in this item, and we can try to predict this link and make corresponding recommendations. Also in chemistry, we can model a molecule as a molecular graph with each node as an atom, and we can try to predict the molecular property based on this graph structure. Also in credit application, we can take advantage of the social network of each applicant and try to predict whether his or her credit application would be approved. In GNNs, node representation learning on graphs is a very widely used technique, and it aims to map nodes into a latent embedding space to facilitate various downstream tasks like node classification, link prediction in a lot of applications, like what we just said, recommended system, chemistry, credit application. However, as the original data may contain many sensitive attributes like race, gender, like here we highlight them in red or green, a main limitation of many existing node representation learning methods is that the representations may contain biases towards certain sensitive attributes. And these biases in the recommendations would also bring biases in the downstream tasks. We all know that real-world inequality and discrimination are actually very ubiquitous, and they can lead to serious biases in machine learning. In 2014, there is a team of software engineers at Amazon were building a program to review the resumes of job applicants, but unfortunately, after 1 year, they realized that the system have discrimination against women for technical roles. So Amazon recruiters stopped using that programming anymore due to this discrimination issue. So here we need to be aware that the discrimination can exist in different forms in real world. The key here is try to improve the fairness in machine learning in the next generation of machine learning. So here we try to use some techniques to mitigate the biases of model predictions against certain subpopulations regarding the sensitive attributes. And here is a general category, a general overview of all the categories of fairness. It's in a survey paper in our group. So recently we have developed a lot of different definitions and notions for fairness, because we noticed that there are a lot of different applications, scenarios, and purposes. So fairness can actually be different in many different ways. For example, one of the mainstream of fairness is group fairness. Well, the high-level idea is there should not be any biases towards any specific sensitive group. Like a famous fairness notion in the category of group fairness is called demographic parity. Basically, it's try to guarantee that in the two different sensitive groups, like male or female, the prediction should remain the same distribution. However, this is a group level fairness notion, and there is another mainstream of fairness notion called individual fairness. The high-level idea is that similar individuals should be treated similarly, that they should have similar prediction results. But all these fairness notions have a limitation because they are defined based on only based on the factual data. However, maybe we can consider a more natural question of fairness, like what if? So people will think about what if my gender or race have been different? Like, will my application get approved if my sensitive attribute had been different? This is a motivation of counterfactual fairness, which is defined from a causal perspective. Well, counterfactual fairness tries to compare the predictions of each individual from the original data and its counterfactuals with different values of the sensitive attribute. For example, the prediction for one's loan application being approved should be the same regardless of this race information being black or white. So here I will first introduce some general background information about causal model. Causal model can be considered as a widely used framework to describe the causal relations between variables in data. Here I will introduce a very famous one, structural causal model, which consists of a causal graph where it is directed acyclic graph with each node represent a variable and each directed edge represent a causal relation. Like there's a little story like race can causally influence the job and the wage. Also, we have ability. It is a fail variable. It can also influence the job and wage, but usually if we directly take all the data into training of the machine learning training process of the machine learning model, then we will probably get a biased result because race or job and wage, this kind of information are all biased. So causal graph describe this, so causal model use a causal graph to describe these causal relations between variables. For the variables, we have the independent exogenous variables like U here associated with each endogenous variable. Usually there are some variables with semantic meanings like race, job. Here we give a formal definition for counterfactual fairness. Well, given each individual with its certain features, I mean, non-sensitive features and sensitive attributes, the value of prediction should be the same no matter how its sensitive attribute had been changed to different values. Here, the A's left arrow, A's means the intervention on the sensitive attribute A's. We just intervene it and set it to different values, but in this process, maybe some other variables will also be correspondingly changed due to the causal relations. Like when we change the race information of a specific individual, his or her address or job application results may also be influenced correspondingly. But after this process, the prediction for the the same individual should also remain the same to achieve counterfactual fairness. This is the definition of it. So most of existing work of counterfactual fairness only focus on regular ID data, but recently there are also a few works try to extend this notion on graphs. Initial exploration here is try to flip the value of the sensitive attribute on the for all the nodes on graph. Like if this person is male, we flip its gender information to female or some other chance, but we need to get the same prediction for the different versions of each individual. However, this kind of way may have some limitations. Like in graphs, the sensitive attributes of each node's neighbors may also causally affect the prediction with respect to this node. Like we have the causal graph here. Well, ij means two nodes on the graph. We have its sensitive features. We have their other features like address. We have their social relation. We have their prediction target, loan approval. And we should notice that the neighbor's sensitive attribute may also influence the features of each node and also the prediction target of this node. This is a very unique property on graph. And here we should notice that after we flip the value of sensitive attribute, the features, like we highlighted them in yellow, the features of other neighbors may also be correspondingly influenced. And here, another limitation of the of that way is that the sensitive attribute may also causally affect other features and the graph structure. Here we highlight these causal relations in green. And after we flip the value of the sensitive attribute, the graph structure, all the features of this perturbed individual would also probably be changed. So considering these cases in this paper, we propose a fairness notion to extend the counterfactual fairness notion on graphs. Here, an encoder should satisfy graph counterfactual fairness if for any node, its learned representation stay the same, regardless how we perturb the sensitive attribute value of itself or any other nodes on the graph. So here we, given the feature nodes and the graph structure, and we intervene the sensitive attribute of any nodes on the graph. If we have n node on the graph, we can set the sensitive attribute values of the n nodes as a random and dimensional vector, but the node representation of each node should always remain the same regardless of these perturbations. For example, the prediction for one's loan application being approved should be the same regardless these applicants and his or her friends raise information. Here is an illustration of the proposed framework. We aim to learn node representations on graphs towards graph counterfactual fairness and maintain a good prediction performance simultaneously. This framework mainly contains three components: subgraph generation, counterfactual, data augmentation, and fair representation learning. First, we should know that the true causal models for graph data are often very difficult to be completely obtained, especially for those large-scale graphs, because you need to consider the causal influence between different nodes. Well, based on a common observation, fortunately, each node is mostly influenced by its nearest neighbors. So for each node, we consider it as a central node and try to extract a subgraph, including the top k important neighbors for this node based on a pre-computed importance score. So we can split the whole graph into many different subgraphs and try to improve the efficiency. And based on the subgraphs, we develop a counterfactual data augmentation module. We try to generate the counterfactuals for each subgraph with respect to different values of sensitive attributes for all the nodes in this subgraph. Generally, we use a graph variational autoencoder, or VAE. With an encoder maps the node of the subgraph into embeddings, and the decoder will reconstruct the subgraph with these embeddings. Here, a fail constraint is used to remove the biases in the embedding. And here, counterfactuals are generated by changing the sensitive attribute of the central node, where we call it self-perturbation, and also changing the sensitive attribute of neighboring node. We call it neighbor perturbation. After these perturbations, we feed this perturbed version into the decoder and try to generate corresponding perturbed subgraphs. Then this is the whole process of counterfactual data augmentation. We will train it first as a separate model and generate counterfactuals and use the generated counterfactuals into the next step. We should be aware that this is based on very general and abstract causal model, and we actually do not assume that we have sufficient causal knowledge about the causal model. So if we actually have some prior knowledge about the causal model, then it would be better we can replace the counterfactuals for later steps and do not need to change other components in the framework. So this is the reason why we split the whole process into the two parts, like counterfactual augmentation and the fail node representation. We just try to make this whole pipeline more disentangled. Then, based on the augmented counterfactuals, we try to learn fail representations which can achieve same predicted label across different counterfactuals with respect to the same node. And here, the prediction, the loss function includes two terms. First, the prediction and the failure loss. The prediction loss encourages the learned representation to achieve a good prediction performance. This is a very normal loss term. And to learn fair representations, we first use a Siamese network to obtain those representations from the original graph and its different counterfactuals. These counterfactuals include both self-perturbation and neighbor perturbations. And the fairness loss enforces the learned representations from the original graph and the counterfactuals to be the same. So we have Zi as the learned node representation for node I from the original graph, and the I bar and on the underlined Zi represent the learned representation from the counterfactuals, and we just enforce them to be as close as possible. Then in the experiments, we have three data sets. The first one is a synthetic graph, and the other two are real-world graphs with real-world sensitive attributes. We evaluate our model in two aspects, fairness and prediction. For prediction, we just use some normally used metrics like accuracy, F1 score, and in fairness, we first also use some widely used fairness metric in group fairness, including data SP and data EO. They are just the statistical fairness metrics try to guarantee or try to measure how much the prediction is fail in the group level. And then we try to use some graph counterfactual fairness metrics, but as this is the first work in this area, so we develop some, we propose some metrics with respect to this specific problem. And here, the way we define the graph counterfactual fairness metric is to measure the difference of the distribution of the prediction after we made random intervention on the sensitive attribute value of any nodes on the graph. As there are a lot of choices, if we have a binary sensitive attribute, we will have an n node graph. We will have exponential level of counterfactuals. So it is a very large scale metric. But to simplify this computation process, we try to approximate it, and we compute it on some certain types of counterfactuals. More specifically, we use some sampling process to generate counterfactuals with randomly perturbed certain percent of nodes, and we will do an average over all these different perturbations. Then also we compute R-square to measure how well the prediction for any node I can be explained by the summary of the node I's neighboring sensitive attribute values, which reflect the statistical dependency between the prediction for each node I and the sensitive attribute values for all its neighbors. So in the experiments, we compare our framework with other baselines. Our framework here can achieve comparable prediction performance as state-of-the-art node representation learning method. And in fairness, GIL performs well in different fairness notions, especially outperforms all the baselines in graph counterfactual fairness, especially in these two metrics regarding the graph fairness. After that, we try to conduct some ablation studies by removing some components in the framework. We remove the self-perturbation or neighbor perturbation and remove all the perturbation and try to use no counterfactual augmentation. Then we observe the variance of this all of these variants underperform the final fair framework. So it validates our conclusion that different components in our framework all contribute to the final performance. Then to investigate the model performance on the different options of model structure, we also vary the encoder of the subgraphs, because our framework can actually be very flexibly adapt to different encoders like GCN encoder, GraphSage, Informax, Jing, Jumping Knowledge. We try to compare different encoders and find all the subgraph encoders show good performance in both prediction and fairness. And generally, GraphSage encoder shows the best performance in our observation. Last, to evaluate the robustness of our framework on the different parameter settings, we vary the parameter lambda, which is the weight of the constraint for graph counterfactuals, and lambda s, which is the weight for neighbor perturbation, and the subgraph size k and the number of neighbor perturbations c in the sampling process to investigate how the model performance varies. Then we have the observation that when we increase the weight of fairness constraint, the model achieves better fairness with slight sacrifice of the prediction performance. And the model can achieve better fairness performance with relatively larger subgraph size. When we change the number of neighbor perturbations in the sample process, when it becomes larger, the predictions also become more fair. All these observations match our intuition. When we come to the conclusion, first we propose a new fairness notion, graph counterfactual fairness, and then we propose a novel framework here to learn node gravitations towards graph counterfactual fairness. And we conduct extensive experiments to show that the proposed framework outperforms existing baselines in different fairness notions and can achieve comparable prediction performance. I think there are still a lot of future work left to do, like we can consider more complex causal models, and we can investigate how the graph counterfactual fairness be influenced with different levels of prior knowledge regarding the causal model. Especially, we can also track the propagation of the biases in the graph to better mitigate or selectively mitigate the biases. We thank these funding agencies, and there are some references which includes this paper and also a survey paper in our group about fairness in graph mining and other very useful references in this area. Thank you for listening, and I would be more than happy to take any questions.
Yeah, thank you so much. That was such an interesting